Hello everyone, hope you're all well. Today we're going to talk about a new learning model, very famous, known as decision tree classifier. This is the outline of the lecture. So the basic idea of decision trees is that it allows a classification of an instance by asking a series of questions, similar to the 20 questions game if you know it. The objective of decision tree learning is to learn a tree of questions, which determines class membership of a given instance by following three branches. Let's look at an example. This is for the dataset we used in last lecture when we talked about naive bias classifier. The idea was to decide whether to play tennis or not based on the weather. So we had four features: humidity, outlook, wind, and temperature, and based on the values of these features we determine whether we should play tennis or not. So in this decision tree we look at the outlook. If it's overcast, then the decision is to play tennis. However, if it's sunny, then we check humidity. If it's normal, then yes, play tennis. If it's high, then don't play tennis. If the outlook is rainy, then look at the wind. If it's windy, then do not play tennis. And if it's not windy, then play tennis. Okay? Now, given test instances, so say the weather today or tomorrow, I want to decide whether I should play tennis or not. So all I have to do is follow the branches of the decision tree. So I look at outlook. Since it's sunny, I follow the leftmost branch. And I have to look at humidity. So humidity is normal. This tells me, yes, play tennis. For tomorrow, the outlook is rainy. So I look at wind. Since it's windy, I decide not to play tennis. So given a decision tree, how to classify test instance, we did this using an example. The idea is to start at the root node and apply the test condition to the instance and follow the appropriate branch. If this leads to an internal node, again apply test condition and follow the appropriate branch. Otherwise, if it's a leaf node, then I assign the class of the leaf node to the instance. Repeat until a leaf node, and that's it. Now, the more interesting question is, how do I build a decision tree from a data set? So again, our setting is as follows. We're given an input space consisting of the features x1, x2 till xd. For example, the temperature, the outlook, the wind, and so on. And a data set which contains of n examples. Here we'll talk about multi-class classification, since it nicely applies to decision trees. So easily applies to decision trees without any need for doing a binary classifier first and then use multiple binary classifiers. Okay, so the basic algorithm for building a decision tree is a divide and conquer algorithm. So I select an attribute for the root node, and we're going to talk about the selection criteria for that. And then I create a child for each possible value of the attribute, split instances into subsets, one for each child based on the attribute value, and repeat recursively using only instances at each child. And I stop the recursion for a node if all instances have the same class or the remaining feature values are the same, in which case I use the majority class label at the node level. So let's look at an example. Here is our dataset from previous lecture. I have 9 instances that are yes or +1 and 5 instances that are no. Here's one possible decision tree, the one we looked at previous slides ago. Here's another possible decision tree where we start with the temperature, check if it's hot, mild, or cool, and follow the appropriate branch based on that, and so on. There are exponentially many decision trees for a given data set. Finding the optimal tree is computationally infeasible, so NP hard. Optimal in what? Optimal in the tree size. the smaller the tree is, the less likely it is overfit to the data. So basically we want to get smaller decision trees as much as possible. So to be computationally tractable, we're going to use greedy algorithms, of course, by doing a series of local split operations to build the tree. It might not be optimal, but efficient algorithms that produce sufficiently good trees exist. So let's look at the model. Again, we want to build a simple tree. At each step, I pick the attribute or feature that will result in separating the data as much as possible. Meaning, right, I have the classes are separate, right? That is, each successor node is as pure as possible. Highlight is here on pure. To measure the impurity at a node T, we're going to compute something called the entropy, E of T, as follows. E of T is summation from k equal 1 to k, where k is the number of classes, probability of k given T, log probability of k given T. And we'll see how we estimate these probabilities. So Pk of T is the fraction of instances that belong to class K, at node T. Let's look at an example. Outlook attribute. So outlook equal to sunny. We have 3 examples, yes, and 2 examples, no. So the entropy of outlook equal to sunny is 3 minus 3 over 5. I have 3, yes, divided by a total of 5, log 3 over 5. Minus 2 over 5, log 2 over 5, which is 0.971. So the purity of this attribute is 0.971, or impurity, rather. Outlook equal overcast. We have 4 examples, yes, 0 examples, no. So what would the entropy be? Exactly, minus 4 over 4, log 4 over 4, and minus 0 over 4 log 0 over 4. We assume log 0 is 0, and log 1, of course, is 0. Here, the impurity or the entropy is 0. Note that this is a very pure split because we have all the examples belonging to one class. Another, for outlook equal rainy, I have 2 examples yes and 3 examples no. What is the entropy going to be? Minus 2 over 5, log 2 over 5 minus 3 over 5, log 3 over 5. So it's similar to outlook equal sunny, and it's 0.971. Okay? So let's look at what is the meaning of entropy. We'll look at the case of 2 classes only, so k equal to 2. As you see, entropy is equal to 0 when T contains only instances of one class. So here, right, it's equal to 0. Here, the entropy is equal to 0 when I have the pk of T is equal to 0 or pk of T is equal to 1. Okay? And it's equal to 1 in the middle, right, when T contains equal instances of both classes. So it's very impure. So entropy computes the impurity at a given node T. How would we use it to pick the attribute that will result in the best split? The best split, we want, right, ideally to have instances belonging to one class. Yeah, a majority of the instances belonging to one class. So at node T, assume that we split using attribute xi into mi child nodes vj. Okay. We compute something called the information gain of attribute xi as follows. Information gain of xi is the entropy of the node T minus summation from j equal 1 to mi and j over n entropy of Vj, where Et and EVJ are the entropy at nodes T and Vj respectively, N and Nj are the number of instances at nodes T and Vj respectively, and the goal is to maximize the information gain. So I want to maximize the information gain. This is equivalent to minimizing the average impurity or entropy of the child nodes. Okay, so this is all too abstract. Let's look at an example. Okay, let's assume I'm looking at the attribute humidity. So we have, overall, we have 9 plus instances. So 9 yes, play tennis, and 5 don't. And the entropy is 0.940. It's minus 9 log 14 minus 5 minus 9 over 14 log 9 over 14 minus 5 over 14 log 5 over 14. Okay? Now, humidity has two values, high and normal. Okay, if I look at high, so when humidity is high, I have 3 examples plus and 4 minus, and the entropy would be minus 3 over 7 log 3 over 7 minus 4 over 7 log 4 over 7. That's 0.985. And when it's normal, the entropy is 0.592 because I have 6 examples plus 1 minus. So the entropy in this case is lower because I have a more pure split. Okay, or a more pure node. So the information gain of humidity would be 0.940, okay, minus 7 over 14. So I have 7 examples. When I split using high, divided by a total of 14, times the entropy of high, which is 0.985, minus 7 over 14, and I split on normal, right? So I have 6 plus and 1 minus, that's 7, divided by a total of 14, times the entropy, which is 0.592, and humidity is normal. So the information gain that I acquire by splitting on humidity is 0.151. Okay, let's check another attribute. So for wind, I have weak or strong, or windy or not windy. When I split wind equal to weak, the entropy is 0.811 because I have 6 positive examples and 2 negative examples. When I split on strong, I get the entropy to be 1. Why? Exactly, because I have 3 plus instances and 3 minus instances, so equal number of instances in both classes. Okay, so the entropy is high in this case. Okay, what is the information gain for wind? It's going to be 0.94 minus 8 over 14 times 0.811 minus 6 over 14 times 1. Right? And that's 0.048. So the information gain for humidity is larger than the information gain for wind. I can also compute the information gain for outlook, which is 0.246, and the information gain for temperature, which is 0.029. Okay, which one had the highest information gain? It's outlook, so I should pick this attribute greedily as the attribute to split on first. Okay, so when I split on outlook, right, so outlook is selected at the root node. I have the outlook is either sunny, overcast, or rainy. When it's overcast, I have all the instances belonging to one class, so yes, play tennis, and I can stop splitting there. For the other 2 nodes, I have to split further, because the instances belong to the two classes that I have. Okay, so now let's look at the next best attribute. It happens to be temperature when the case is when outlook is sunny, and I have temperature is hot, mild, or cool. When it's hot, I have all the instances belong to the no class. When it's cool, all the instances belong to yes. It's one instance, and when it's mild, I have one yes and one no. I can compute the information gain of temperature, that's 0.571, as we did in the previous slide. I can try also humidity, right? For the case outlook is sunny. I have 3 instances when humidity is high in the no class, and 2 in the yes class for normal. Information gain is obviously high here because I have a better split, so it's 0.971. And I can try outlook. For outlook sunny, I try the wind attribute, and I have 2 splits, false or true, so I get 2 nodes, and neither of these nodes are internal nodes, right? And the information gain of windy is 0.020. Which attribute should I pick now to split on or to use in this internal node? Outlook sunny, of course, the humidity. Okay, so I pick humidity, and I have right to leaf nodes or pure leaves, so I don't need to split further, right? Now for outlook rain, I still have to split because this is an internal node. It doesn't have pure. It doesn't have instances belonging to one class only. Okay. So for rainy, I look at wind, right? I can try the same exercise. So try temperature, try wind, try humidity, and I realize that wind has the highest information gain, and I get 2 leaf nodes. When wind equal to false, yes. When wind equal to true, no. Okay, that's pretty much it. Now we're going to talk about some practical considerations. There are many alternatives to entropy. So there's the Gini index, which is given by the formula shown here. There's classification error. Similarly, there are alternatives to information gain. For example, information gain ratio, which is the ratio of information gain to the intrinsic information. And this is used to reduce bias towards multivariate attributes by taking the number of children on the side of their instances into account. So information gain tend to favor attributes with a lot of values. The information gain ratio addresses this. How do I deal with continuous attributes? Similar to naive Bayes classifier, when I have continuous attributes, things are a little bit more complicated. So the standard method is to do binary splits. So I can say, for example, temperature is less than 45. However, unlike nominal attributes, every attribute has many possible split points. So solution is straightforward extension. Evaluate information gain for every possible split point of the attribute. Choose the best split point. Computationally more demanding, of course. But let's look at an example. So temperature is a continuous attribute, as we know. So first step is to sort all examples according to the value of this attribute. So I sort them in this table, right, based on temperature, and I have the label of every instance. Okay. And then I try one split between each pair of values. So temperature less than 71.5, I have 4 yes and no 2. Temperature greater than 71.5, I have 5 yes and 3 no. I can compute the information gain of temperature. That's 6 over 14. Entropy of temperature less than 71.5 plus 8 over 14 entropy of temperature greater than 71.5. Of course, this is subtracted from the entropy of the parent node. And then I repeat this for other split points, and then I pick the split point that gives me the highest information gain. Now, common problem with decision trees is overfitting, i.e. the tree might be too tightly tailored to the training data. That's a problem. And the solution is there are various solutions. One is early stopping. Stop growing the tree when the data split is not statistically significant. Or doing pruning. So build a full tree and then prune parts of it. So early stopping. The normal stopping condition for splitting a node if all instances belong to the same class or if all the feature values are the same. In this case, we use the majority class. So early stopping works as follows. You stop splitting a node if the number of instances is less than some predefined threshold. You stop splitting a node if all remaining attributes are not significantly correlated with the class. And you can use a chi-square test to verify this, for instance. Tree pruning. You build a complete decision tree. Trim the nodes of the decision tree in a bottom-up fashion. So split data into training and validation set or use cross-validation. Remove one node at a time and evaluate the performance on the validation data, or compute cross-validation error, or remove the node that decreases the error if any. That's pretty much it. You can now use decision trees in any of the libraries that implement it. There will be no assignment on naive Bayes or decision trees directly, but you will encounter them as models you should test or use in later assignments or in your project. Okay, thank you.